Okay, good morning, everyone. I'm Ben Sachs. For those of you who don't know me, my company, Sachs & Associates, offers training in C and C++ for programmers and companies all over the world. And I'm going to be talking today a little bit about exception handling. And before we dive in, I want to make sure that we're all on the same page about what we're talking about, because exception is one of these overloaded terms in programming, and it's easy to get confused when you're talking to someone else. So when C++ programmers talk about exceptions and exception handling, they're generally talking about synchronous program errors, things like failing to allocate memory or suddenly discovering that a value is out of range, things that happen within the normal band of the program. If you're talking to a systems engineer, they often use terms like processor exception, which might be interrupts or instruction traps, things like that. That's not what we're talking about today. We're talking about exception handling in C++. The purpose of exception handling is to separate the thing that reports an error condition from the thing that actually handles an error condition. Because as you'll see, generally speaking, the person who discovers that something is wrong is not necessarily in the best position to do something about it. So let's talk about the world a little bit before we had exceptions. So C doesn't have exceptions, so many of its standard library functions have to report any failures that they might experience in other ways, like using return values or in some cases arguments. So for example, the malloc function from C tries to allocate memory. If it can't, it returns a null pointer. You have to check to see what the return value is to make sure that you actually got the memory you asked for. If you call printf and it can't actually write out all of the things that you asked it to print, the result is it returns a negative value. If you call the strtol function, this one's actually a little bit more complicated. The purpose of this is to convert a string into a number, to parse a number out of a string. And it might run into a situation where the number in the string is too big to fit in the unsigned long that we asked it to return. In which case, this function, it returns ulong max, but it also sets a global flag called erno to a value called erange that you can then test for. So these are the sorts of mechanisms that people used to use before exception handling was available. And it works, but to some extent. But it can be cumbersome and difficult to do because, as I mentioned, often the function that detects that something is wrong is not the function that can actually correct when something is wrong. That can actually correct that condition. It's usually not even the caller of that function. So here's an example program. What you're going to see is we have a main function that calls a function f that calls a function g. And if we didn't have to worry about failure at all, if we knew that everything was always going to go right, the program would just look like this. So we have main, it starts by calling f immediately calls g does whatever it needs to do, it returns back to f finishes whatever work it needs to do, and then it returns back to main, which performs the rest of the program. But of course, in the real world, errors do occur. So let's say that G can encounter some sort of failure that it can't immediately handle itself. In that case, we probably need to change G, assuming we don't have exception handling for the moment. We would need to change G so that it had some sort of non-void return type like an int, and then we could use separate return statements for returning error conditions or normal return values to indicate success. So the function might look something like this. G now has an integer return type. We check to see if some really bad condition exists. If it does, we return a -1 as an error indicator. Otherwise, we go on, execute the rest of the function, and return a 0 to indicate success. Oddly enough, 0 was usually used in these cases to indicate success, because you might need to talk about different kinds of failure. And so you have several different values that represent different error codes. And then what's the one that's left over that doesn't look like the others? It's 0. So then there's a good chance that f doesn't actually know how to respond to this failure. It might, and if it does, it could just look at the return value of G and handle it. But let's suppose that F doesn't know what needs to be done. Suppose it's main that actually deals with the condition that G discovered. In that case, F needs to be changed so that it checks for the return value from G and just returns that value further up the call chain until you find someone like main who can handle it. So now we have to add in, you notice all this code in red is new here. We have to record the return value of G, check to see whether it was 0 or not, and if it wasn't, if it was some sort of failure code, we return it back to the caller. Otherwise, we keep going and then return success when we're done. And then main looks like this. It can check the return value of F, and it can actually handle the error in this case. So this sort of thing can work. By returning these error codes, we have in some sense decoupled the person who detected the error, G, from the person who actually handles the error, main. But it's kind of tedious. You saw how much code I had to introduce to make sure that that was the case. And here we're dealing with a call stack that's 2 functions deep. It's not uncommon for it to be 20 functions deep or 200 functions deep in some large programs. So you can imagine the amount of extra code that winds up being generated to deal with these sorts of error conditions. And it can really clutter up the program, makes it much harder to read and get a good sense of what's going on. It's also kind of fragile because anywhere in that chain, if I forget to check for a return value and pass it on to my caller, then the whole chain breaks down and failures go unreported and my program does something weird as a result. And we get the joy of debugging it through some complicated process. So exception handling was an attempt to fix some of these problems. It's not original to C++, but introducing it into C++ was intended to help solve some of these issues. So the idea is that errors are treated as exceptional events that are handled out of band, not exactly within the normal control flow of the program. And so as the programmer, when an exception is thrown, what we see is pretty much that control is transferred directly to the person that can handle it, and it doesn't, to our eyes, it doesn't appear to go through all of the intervening steps. It actually does. I'll talk about that in a little bit more later on, but you don't have to deal with the clutter that I just described. So we have these 3 keywords, throw, catch, and try. So throw throws an exception. Big surprise. The value of the exception can be the value of any expression like that, but as long as, and whatever value we choose is meant to convey some sort of information about what kind of failure occurred. Now, you can throw exceptions of any type. Usually we don't throw primitive types like int or double. We throw objects of class types, as you'll see. So the standard library in C++ has a number of pieces that can throw exceptions. And in particular, they throw exceptions that are all derived from a common base class called exception. Well, std : exception because it's in the std namespace. And that exception class is defined in the standard header exception. The others are actually defined in a separate header called noexcept. Now, often you don't need to include this one directly because if you're including a standard library component that throws these things, it's going to include that for you. But if you want to build on the existing exception hierarchy that the standard provides you, this is where you would find those classes. And they have names like invalid argument, out of range, overflow error, and these are all derived from that common base class exception. They're not all in noexcept. There are a few other standard exception classes in the headers new and type info for dealing with specific problems. But all of these you'll find in the namespace std. So that's how you throw exceptions. How do you actually handle them? You write a handler like this. It's sometimes called a catch clause because it uses this catch keyword, throw and catch. The catch clause looks like this. We have an exception declaration. That's the thing that states what kind of exception we're trying to handle here. And then we have just a block of code, a sequence of statements that can be any code we want that responds to the error condition in whatever way is appropriate. That exception declaration looks pretty much like a function parameter. So here, for example, is a catch block that can handle standard out-of-range exceptions. Since we have a common base class for all the standard library exceptions, we could also catch std exception in general. And that would handle any standard library exception. Notice that I'm catching these exceptions by reference. Usually, what we do is we throw by value and we catch by reference. That's almost always what you want to do. So, where can I put these handlers? How do I know what code the handler is handling exceptions over? That's defined by a try block that looks like this. So you write the keyword try, and then you have a block of code inside the try block. That's the code that could potentially throw exceptions. And then after that try block, you write a sequence of one or more catch blocks in this handler sequence. And those describe what kinds of exceptions you're going to handle and what you need to do about them. So it winds up looking something like this. So here we have a function f that wants to call the functions g and h. And it knows that somewhere in the process of calling g and h, it's possible that an out-of-range exception might be thrown. So it wraps g and h in a try block like this. And then below the try block, it places a catch block that states that it can catch an out-of-range exception. And then the code in that catch block then responds to the out-of-range exception in whatever way we need to do. If it's G that throws the exception, we never wind up going on to call H. As soon as the exception happens, control is transferred immediately to the catch block. This is what I was talking about when I meant that it was sort of out of band. It interrupts the normal program flow. So let's take a look at, earlier I showed you main calls F, calls G, which could report a failure. Let's take a look at what that's going to look like if we use exception handling. And in this case, I'm going to use a class of my own design called catastrophic failure to represent the exception. So now G changes so that if it detects the error condition, instead of returning a -1, it throws a catastrophic failure object, and it just constructs that catastrophic failure object right within the throw statement. This is a very common thing to do. So now G can go back to just returning void, because it no longer needs to use its return type to report failures. It has exceptions for that. F goes back to just looking like this, because now F was never in a position to respond to the catastrophic failure. It never knew what to do if G failed. So F doesn't check for the return value of G. F has no handlers. And when the exception is thrown out of G, we see that the program sees that there are no handlers in F, and the exception just propagates out of F and keeps searching up the call stack, looking for something that can actually handle that exception. And in this case, that's main. The main function has our try block wrapping around F, and it has a catch for catastrophic failure, where it then handles the error. Now notice, it was G that threw catastrophic failure, but from the point of view of main, it's an exception thrown from F. Main can't tell the difference whether it was F or G that threw the exception, and it doesn't need to know. It just handles an exception that occurred somewhere down the call chain. So, in general, the rule is this. If you have a function like G that doesn't have any handlers in it and it throws an exception, the first thing that happens is that all of the local objects within G, any local variables, are destroyed, which usually means they have their destructors run. And then, once all the local objects are destroyed, the program searches back up the call chain. It transfers control back to G's caller, F in this case, looking for something that can handle the exception. In this case, F doesn't have any handlers either, so the process repeats. We destroy any local objects inside of F, and then we search back up the call stack once again, going to F's caller, looking for something that can handle the exception. And it just keeps searching, it keeps searching until one of two things happens, which I'll talk about in a moment. So what I want to make clear first is that this is also true if F contains a handler, but not a handler for the type of exception that's actually being thrown. So here, F has a try block around G, but it's not prepared to catch catastrophic failure exceptions. It's prepared to catch out-of-range exceptions. So it can't handle a catastrophic failure. If G throws an out-of-range exception, it can handle that. But if catastrophic failure is thrown, that's not one of the exceptions that can be caught here, so it just propagates out of F as if there hadn't been any handlers there at all. And this process just repeats until we either find a handler that can actually handle the exception, or we get to the main function. If we get to the main function and the exception would propagate out of main, then what happens is a standard function called terminate is called. And it does what you'd pretty much expect with a name like that. It terminates the program. It shuts it down, and then what you usually see on most platforms is one of those mysterious dialog boxes pops up that says unhandled exception or uncaught exception at some address that would presumably make sense to you if you were the programmer of that program. So, in this case, let's talk a little bit about designing interfaces around exceptions. So, suppose that G can only throw catastrophic failure for the moment. And now let's look at a version of F that's written that can actually catch and handle catastrophic failure. Now, if I'm the author of F, at this point, when I've written this function, I think I'm handling all of the exceptions that G can throw. So what happens if G is then changed so that it can also throw out of range? I'm realizing now that I probably shouldn't have used out of range in this example because before F could catch out of range. But in this case, F is only catching catastrophic failure. So since F doesn't contain a handler for out of range in this case, if G throws out of range, it propagates through F. And F's caller now sees F throwing an out of range failure. And if F wasn't prepared for G to throw an out of range failure, it's probably true that F's caller wasn't expecting F to throw an out of range failure either. So you want to be careful about choosing what types of exceptions a function can throw. This is something that you think about when you're writing the interface up front. You determine what a function can throw, and you should be hesitant to change that list of things that the function can throw, because it's easy for this kind of thing to get out of hand. F or G could be called in lots of different places, and you could have a lot of code that needs to be modified to respond to the possibility of new error conditions. And there's not much that the compiler can do to help you in this situation. It's not like when you change a function's parameter list, and often, in that case, calls to the function just don't compile anymore. In this case, you won't know until an unexpected exception was thrown, and then somewhere in the program, it gets caught or it doesn't, and you terminate. Now, you can actually specify that a function never throws at all. You can use this noexcept keyword to do that. Now, just to be clear, you want to be careful about declaring functions as noexcept only if you're sure that they really don't throw exceptions. Because this isn't actually enforced at compile time. The compiler doesn't check to see that that nothing further down the call stack actually throws exceptions. What happens is if a noexcept function actually throws, it's checked at runtime, and the result is that terminate is called immediately. So you really want to be sure in this case that your function doesn't throw exceptions because we don't want to terminate unnecessarily. Now it turns out you actually can catch any kind of exception at all by writing a catch block that looks like this. It has an ellipsis in the catch instead of a declaration for a specific type of exception. But the thing is, at that point, you don't know what kind of exception you caught. It's difficult to do very much in this block because you can't actually look at what kind of exception you're dealing with and refer to it and do specific things based on a specific kind of exception. So what use is this? What you typically see people do with a block like this, as you'll see, in practice, these are rare. You often don't need to write these, but what you often see people do when they write a block like this is that they're actually not trying to handle the exception completely. What they're trying to do in this case, what this catch block does, is it notices that an exception is being thrown. It cleans up some local resources by calling delete on a pointer that otherwise would have resulted in a memory leak, because when the exception was thrown, we would miss the delete somewhere else in the program. And then we proceed on to, and then the next statement there throws the caught exception again, resumes throwing it up the call stack looking for someone that can really handle the exception. So notice that throw there doesn't have an operand. It's just throw semicolon. What this is a statement that can only appear inside a catch block, and what it means is rethrow whatever exception I caught before. So it's particularly useful in this case where you don't have a name to refer to the exception that you caught because you don't know what type it was. Now, another thing that we could do in this sort of situation, instead of rethrowing, we could catch an exception of one type, deal with any local cleanup, and then translate that exception into another type of exception, like we're doing here, where we catch an overflow error, but we actually the next thing that we throw further up the call stack is an invalid argument. The idea here being that in the context of this function, further down the call stack, something caused an overflow error, but this might be an appropriate thing to do if the overflow we think was caused by someone passed a parameter into us that turned out to be invalid and caused that overflow. And this sort of thing, translating exceptions like this, can be helpful for keeping the list of exceptions that a particular function throws stable, for making sure that you don't regularly change the list of things that can be thrown. So that covers sort of the mechanics about how you actually throw and catch exceptions. But it turns out that writing code that works really well in the presence of exceptions is often not so much about writing those three keywords, but rather setting your code up in such a way that it doesn't need to know whether an exception is being thrown or not, but it will respond appropriately if whether or not an exception is thrown. This is what we call writing code that's exception safe. Actually, what I just described is a slightly different thing. Code that doesn't look at exceptions at all is exception neutral. And exception safe, code can be both exception neutral if it doesn't notice exceptions, and exception safe if it responds correctly even if exceptions are thrown without having to check. So we talk about exception safety as having three different kinds of levels. There's the basic guarantee, the strong guarantee, and the no-throw guarantee. So what are each of these guarantees that a function could make to describe itself as exception safe? So the basic guarantee is this. The function might throw an exception, and if it does, it's possible that something has happened during that function that changed the state of the program before the error condition was detected and an exception was thrown. But however the program state changed, the program is in a logical state. It's not necessarily the same state that it was in before you called the function to begin with. But throwing the exception hasn't caused any resource leaks, and we haven't corrupted the state of the program in any way. Like, we can't have an object of type circle that says it has a radius of 0, but an area of 5. That's illogical. That doesn't make sense as a circle, but data corruption could produce something like that. The basic guarantee says that won't happen. The strong guarantee says the function might throw an exception, and if it does, the program's state is the same as if you'd never called this function to begin with. No changes to the program's state are made before the exception is thrown. In other words, the function has commit or rollback semantics. If you've worked with databases, you might be familiar with this. Often you wrap database interactions up into transactions, and if the whole transaction fails, it's as if you never tried to do the transaction in the first place. Functions that implement the strong guarantee work the same way. If it fails, you're right back where you started. And then there's the no-throw guarantee, which the name implies it just doesn't throw an exception at all, right? It turns out it's actually a little bit more complicated than that. Further down the call stack, it's possible that an exception would be thrown within a function that implements the no-throw guarantee. So an exception might be thrown, but the function that makes the no-throw guarantee is promising it will handle any exceptions that get thrown by any of the functions that it calls. So no exceptions will ever propagate out of a function that makes the no-throw guarantee. An exception might be thrown in the process of calling that function, but the person who called the function that makes the no-throw guarantee, they will never see an exception as a result, because it will always be handled before it gets to the caller. So let's take a look at putting this into practice. What's involved in writing a function that implements one of these guarantees? So here we have a somewhat embellished version of the function f that I was showing you before. This one now takes a parameter that represents the name of a file to be opened and written to within the program. And in this case, I'm using the standard C file object. You'll see why I'm doing this in just a moment. So we open up the file. We check to see, were we able to actually successfully open the file? If we were, go ahead and write out the value of something that will be returned by the function g is x to the file, and then go ahead and close the file. So this function isn't exception safe, because suppose g could throw an exception. If that happens, we will skip over, there's no handler in this function, so the exception will immediately propagate out of f, and we will skip over the call to fclose there. As a result, the file will remain open. We would destroy the pointer out f, but that's a built-in object of type pointer. Pointers don't have destructors. That's why we usually have things like delete paired with new. So in this case, the file would remain open and we'd have a resource leak. So this is why you'll often see C++ programmers, they wouldn't use a basic C file object. They would use one of the new C++ file streams. And that's because those streams behave the way that I'm about to, like the classes I'm about to show you. C++ classes turn out to be really helpful in mitigating these problems because we can use constructors to initialize objects and then use destructors to guarantee that the resources allocated in the constructor will be deallocated in the destructor. And because destructors do run when exceptions are thrown, now we can be sure that things will actually be cleaned up. This is something called RAII. Now, I don't have time to, there was a whole discussion of RAII earlier in the program. Arthur O'Dwyer gave a very nice talk, also another Back to Basics talk, actually talking about RAII and the rule of zero. And so if you want more information about this, go ahead and take a look at that talk. But the basic idea is that anytime you want to acquire a resource, whether that's dynamically allocated memory or a file or exclusive access to some sort of resource, you acquire that resource in a constructor. And then you have a paired destructor in the class type that releases the resource. And then, so here is a basic class called file that that implements this RAII behavior that gives us, that opens the file in its constructor and closes it in its destructor. Then it has a few other functions here for checking to see whether the file is actually open and writing out to it. I'll talk about that in just a little bit. So the constructor looks like this. It calls fopen, puts the results into the private data member PF, that is the pointer to the C file object that we're actually managing. And then the destructor checks to see if the file is still open. It was ever opened in the first place, I should say. That's how we would get a null pointer there. And if we have an open file, it closes it. Now, constructors don't have return types. So what happens if we're not able to open the file in the first place? Because fopen can fail. It returns a null pointer if it does. So we could do something like provide that isOpen function that I showed you earlier. And that just checks to see whether the file was actually opened successfully. And then we can write, when we construct our file object, we can write code that checks to see, did it succeed, and then behave appropriately. Another thing that we could do, though, is we could make the file's constructor throw an exception if it can't open the file. So we could check for the null pointer condition inside the file constructor after we've called fopen. And in that case, we throw something like catastrophic failure to indicate that the file couldn't be opened successfully. Now, if this happens, if a constructor throws an exception, we think of the construction of the object as having been interrupted before it could finish. So we never actually create a file object anywhere. We stop before a file object actually comes into existence. So the destructor for file doesn't run in this case. We never finished building it, so we don't tear it down. What that means is, if you had a class that had a whole bunch of resources that it was managing, what you might need to do is check to see if a failure occurs, you might need to release other resources that you've already allocated. Usually, a better thing than that to do is not do that, to use classes to manage individual resources. And then if you have some larger object that needs to interact with several resources at once, it has data members, and each one of those data members is responsible for managing an individual resource and has an appropriate destructor for cleaning up that resource specifically. So, if we use, here we're using the version of the file class that uses isOpen rather than throwing an exception in the constructor. A lot of people might prefer to use the approach of throwing exceptions in a constructor, but for illustration purposes, I don't want to complicate the demonstration of how we respond to what happens if G throws by introducing the question of, well, but files constructor could also throw. So in this case, we just have one source of possible exceptions, and that's G in this function. So it looks like this. We construct our file object. We check to see whether it was actually opened successfully. We go ahead and write out the value is to the file, and then we proceed to write the value that to call G and write the value that G returns out to the file. So this version of F gives us the basic safety guarantee. The file is always closed. If no exceptions are thrown, we reach the bottom of the function and the file's destructor is called through the normal process and the file is closed. If G throws an exception, then F has no handlers for that exception. The exception will be thrown out of F, but before that happens, the destructors for the local objects will be called, and the file will be cleaned up and will be closed and cleaned up at that point. What would we need to do to make this implement the strong guarantee? Well, there's a general pattern that functions that implement the strong guarantee usually follow, which is you separate the function into two parts. In the first part, you do everything that could possibly throw, and you store the results of any of those operations inside local variables. And so as a result of that, if any of those things that throw an exception, the local variables should all have destructors that can clean up anything that was allocated or any other resources that are being managed appropriately. And the exception can simply continue on being thrown. And because all of the results that we've done so far are in local variables, the program state hasn't been altered. And then part two is to actually update the state of the program, to commit the values from those local variables to wherever they finally need to be. And we need to do that in using operations that we are sure won't throw. Now we'll talk a little bit about how we can be sure that things won't throw in just a bit. Here's a version of F that implements the strong guarantee. So instead of waiting until we're ready to write out the value that we get from G, we call G up front and take the value and store it in a local variable. Then we go ahead, open up our file, so we check to see whether it's open. And now, once we get to the point where we know that the file is safely opened, now we're in the part of the code that can't throw exceptions, and it's safe to go ahead and write everything out to the file, because we know that those write operations will succeed. And now this version of the function implements the strong guarantee, because if G throws an exception, then we haven't done any work, we haven't written anything to the file before we got to that point, and the file remains unchanged. So there are certain functions. The no-throw guarantee in general is something that you see particularly applied to certain functions, namely destructors, operator delete, and swap member functions. It turns out that it's really important that these functions never throw, because if you don't have these functions making the no-throw guarantee, it's really hard to make any other code exception safe.
Excuse me?
Yep.
Could you go back one slide?
Yes.
Is this really a strong guarantee because put could throw an exception?
In this case, I'm assuming that put implements it doesn't throw exceptions. It implements the no-throw guarantee for the purposes of this demonstration. Yes, if I had a more complicated situation, I might need to do other things depending on exactly what I'm doing, and we'll talk about some examples later on where we see other ways of implementing the strong guarantee. But just for this demonstration purpose, I was looking for something that could be the basic function back here, where we would write something because we write the value is before we ever call G, and then could be changed into implementing the strong guarantee without too much difference, as long as we assume that put doesn't throw. So, the no-throw guarantee. So let's suppose we were actually writing a function that was going to read from two files like this. So it takes in the names of both files as parameters, and then it constructs each of the two files, first and second. And then it does whatever it needs to do with those two files to read them. And then when we get to the end of the function, the destructors are called in reverse order. So second is destroyed before first is destroyed. Destructors always run in reverse order of creation. Let's look at what could happen if files destructor could throw. If files destructor could throw and second's constructor can throw because we're not able to get to open the file in the first place, then what happens here? Second is never created, so we don't run its destructor, but first was successfully created, and the exception is going to propagate out of read two files. So we need to call the destructor for first. So then the question is, if we're already in the process of throwing one exception, and the destructor for first throws another exception, what happens? It turns out you're only allowed to throw one exception at a time. And normally this isn't a big restriction because you're not in charge of doing the stack unwinding. The program handles that itself automatically through code generated by the compiler. So you don't have much opportunity to write code that would throw a second exception in response to a first exception being thrown. But destructors are code that you do write that can be called as a response to throwing an exception and unwinding the stack. And if that happens, if a second exception is thrown while a first exception is already being thrown, we immediately call std terminate and the program ends. And we don't want to do that. So it's really important that destructors, as well as operator delete, which is often called in destructors, don't throw. What about the swap member function? Why does that one have to be no throw? I mentioned before that the way that we typically implement exception safety, in particular the strong guarantee, is that we need to be able to update the state of the program using operations that are guaranteed not to throw. So how do I know that I will be able to commit data from my local variables to the places where it actually belongs? And turns out swap member functions make this fairly straightforward in most cases. So here we have a class called little. And we have another class called big that contains two data members, an object of type int and an object of type little. Big has two member functions, munge, which can throw an exception, and swap, which can't. Swap is designed to swap its value with another big object. It turns out it's fairly simple to make sure that this swap function implements the no-throw guarantee, and here's why. The first line swaps the two data members I. I is of type int. Objects of built-in types never throw exceptions. Operations on integers don't cause exceptions to be thrown because they're built-in types. The other line, we have a data member of a class type, little. For data members of class types, we can implement a swap function that doesn't throw, that can swap the values of those class data members. Okay, but how do I know that little's swap function doesn't throw? Well, what could the data members of little be? They could be built-in types, which never throw, or they could be other class types that can have swap member functions that don't throw. Proof by recursion. QED. So now if we write the munge function here, we can make sure that this is exception safe by doing whatever might throw initially and storing that in a little object. In this case, might throw would be something that would eventually result in a change to the little portion of the big object. So we store the new value for our little object inside a temporary object like this. And then, once it's safely stored inside, if might throw actually throws, well, we haven't done anything to change the value of L yet. So the state remains unchanged. Once we've safely stored the result from might throw inside temp, we swap it over to L. And what's really neat about this technique is that now L's old state is now in temp. So when we leave the function, the old state of little is cleaned up by temp's destructor. So we get this really nice behavior of the swap really turns out to be very helpful in implementing this sort of exception-safe behavior. So that covers sort of how we can make functions exceptions safe. So last question I want to address is, when do we throw exceptions? When would we use exception handling? And when would we use other techniques for reporting errors? And there aren't real strict guidelines on this. There are guidelines on this, there aren't real strict rules. It's generally agreed that you want to throw exceptions in exceptional conditions. Things that aren't very likely to happen, but occasionally are the sorts of failures that you need to deal with. You don't want to use exceptions as part of normal control flow. You shouldn't treat them as sort of a go-to that just lets you, oh, I'm going to throw this exception as a quick way of getting back up to some other place in the code. That's not what they're designed for. They're also not a particularly good tool. So far, we've been talking about a lot of situations where the error condition occurs fairly far away from the place where it can actually be handled. If you're dealing with the sort of error that it's reasonable to expect that your caller would be able to respond to, or in fact your caller might be able to check for and guarantee that it can't occur before ever calling your function, that's not necessarily a good use of exceptions. That's a situation where you might want to use a simpler return value and reserve the use of exceptions for really exceptional events. So that brings me to the end of the talk. I'm happy to take some questions. Otherwise, I hope you find this useful. Enjoy the rest of the conference.
So, here's obligatory. Are we ever getting finally, or are we always going to have to deal with objects, wrappers, and destructors?
I don't know of any proposals that would, so the question is, other languages that have exception handling in them have an additional keyword called finally. And what finally does is you put final, let me show you an example, or let me show you where it would be. If we wanted to have finally behavior here, what we would do is after the last catch block, there would be a block labeled finally, and that block is run whether you complete the try block without throwing an exception, or whether you start running the stuff in the catch block, in the try block, you wind up in one of the catch handlers, and then you finish the catch handler, and then the finally it takes effect. This is not a thing that can be done in C++. It's something that can be done in Java and some other languages. C++ doesn't have it because, in general, the things that it's used for in other languages are for doing things like cleaning up resources. And destructors are usually the preferred mechanism for it in C++. I think that using destructors, and many of the experienced C++ programmers that I've talked to about this think that Destructors are in many cases a handier tool for doing this. So I don't know of any proposals to bring finally into the language. You can always, if you just want to run arbitrary code that normally wouldn't be in a destructor, you can always invent a class that just that has a destructor that just does whatever you would normally do in the finally block, but which is not necessarily exactly what you want. But no, I don't know of anything that would add finally to the language.
Okay, and a second, I'm ready to be stoned to death after asking, but the only good thing I think that Java has is it explicitly tells which exceptions the method can throw. Is considered, and you have any thoughts on it?
Yeah, it was actually something that was in the language at one point. It used to be that in addition to being, it used to be that before you could write noexcept, there used to be a keyword that could be placed in this location called throws. And then within throws, you had parentheses, and then you could list out all of the types of exceptions that a function could throw. And this turned out to be, the original intent, I think, was that that could be checked at compile time, and that proved to be very difficult in time. In particular, if this were a function template, and you were dealing with code that could be dealing with objects of any type, it's very hard to anticipate what sorts of exceptions a generic object might throw. And so as a result, the language designers, they didn't mandate that, they didn't say that that the throws clauses were checked at compile time. They had to be checked at runtime. And the result was surprising behavior. People generally assumed that they would be checked at compile time and then were surprised when that didn't happen. And so eventually the throws specifications were removed from the language. And the one thing that was left over was that people found it helpful to know whether a function could throw any exceptions at all. And that became noexcept.
Thank you.
Could you say a word about some performance issues which are connected with throwing exceptions, about unwinding stack and so on?
Yeah, so the question is about the performance of exceptions. And it's a complicated question. The standard doesn't mandate an implementation of exceptions. There are, generally speaking, two common ways to do it. There's what's called a table-based approach, where the compiler generates at compile time lists of information about what behavior, about what needs to be destroyed if exceptions are thrown from specific places, and where those exceptions might go. And then there's the, I believe the other system is I'm trying to remember what it's called. Actually, give me a moment. I have notes on this I had notes on this in a previous version of the talk, and I didn't think I had room for this. So there's the table-based approach, and then there's what's called the dynamic registration behavior, where essentially exceptions are treated as an alternate return path. And as you call down, functions register what things will need to be destroyed if the thing that they're calling throws. If exceptions are, by the way, John Kalb gave a talk at CppCon 2014, I believe, that covers exceptions in more detail than I can get into here. It was actually a 3-part talk on exceptions and writing exception-safe code, and he addresses some of these performance issues. But in general, a lot of work has been done to keep the cost as low as possible if no exceptions are actually thrown. Throwing an exception is generally fairly slow. there is a fair amount of overhead involved in actually throwing exceptions and getting them to the places where they need to be caught. And advances are regularly being made in terms of improving that performance, but it's not clear that they can be, that it will ever be a particularly fast thing to do. In some ways, you shouldn't care, because throwing an exception, if you reserve throwing an exception for exceptional circumstances that are very unlikely to occur, at that point, in some ways, you no longer need to care about performance, you need to care about recovering the state of the program and getting back into a known state. You're not going to accomplish whatever you were trying to do in the first place. So the fact that it's a little bit slow to recover from it is often something that you don't want to treat as an issue. This is another reason why people typically don't use exceptions as part of the normal control flow. But yes, they can be fairly slow and costly to actually throw exceptions, and it's something that you need to watch out for. And it's a reason why, in some environments, people regularly disable exceptions. That's not something that the standard technically allows, but it's something a lot of compilers provide.
Thank you.
Mm-hmm.
Question?
Yeah.
Are exceptions common in safety-critical environments, or are they usually used majorly in library components?
So the question was, I think there were sort of two aspects to that question. You were asking about safety-critical applications, and you were also asking about library implementations. So for libraries, it really depends. Some libraries will throw exceptions, and some libraries will studiously avoid throwing exceptions. And usually, you can tell either by looking at the interface, or in many cases, if you're talking about libraries that would be used in safety-critical code, a lot of safety-critical code is still written in C. And so if you're a library vendor targeting that sort of environment, you're probably going to provide a C library with, at most, a C++ wrapper around that library. And if it's a C library, it can't throw exceptions. So that, in some ways, is a guarantee there. Safety-critical applications usually don't make use of exceptions, because often in safety-critical applications, you need to be able to respond to bad conditions fast. And so the fact that throwing an exception can be slow can be a problem. If the error signal that an exception is meant to represent is to tell a motorized saw, stop cutting, that's flesh. It's not, it may not stop the saw as quickly by throwing an exception as you might be able to through other mechanisms. Now, of course, it's a little bit of a catch-22, because as I mentioned before, one of the reasons that exceptions exist is because they make it easier to make sure that you actually will see the error condition. If you're implementing error reporting through return values, it's possible to make a mistake and just drop the return value on the floor. So, in a safety-critical application, generally the approach that they take is don't throw exceptions, but just inspect the hell out of your code, or test it in a mechanized way that makes sure that if these sorts of error conditions occur, they're handled appropriately.
Thank you.
So you have listed up there the two different ways to implement exceptions, both the table-driven and the dynamic registration method. Are both of those equally as slow, or is it better for one or the other implementation if you're going to use exceptions? be better to choose a compiler that did one or the other?
They have different costs. It's not that one is necessarily better than the other in all circumstances. It depends on how things work. I believe that the general approach is that the table-driven behavior is essentially trading space for speed. It increases the size of your executable by generating lots of data tables at compile time that wind up in the compiled executable that tell the program what to do if exceptions are thrown in certain situations, where to go and what needs to be destroyed. Whereas I believe the dynamic registration approach usually has a higher runtime cost. It introduces more overhead into the general flow of the program, but the actual process of throwing an exception in that situation. The table-driven approach essentially says, we're going to try and make it so that you don't notice any cost if you don't throw any exceptions. The dynamic registration approach says, you'll pay more upfront, but if you actually throw an exception, it's not as expensive as it would be in the table-driven model. I think the table-driven model is more common these days, but it's not universal.
Thank you.
No problem. I'm happy to take any other questions individually, but we're at the end of our time slot. So enjoy the rest of the conference and good luck in your programming.